Hello everyone and welcome to The Public Space. We continue our digging through the rope hypothesis of Bill Gates. Will the rope hypothesis sustain the highest levels possible of gravity, the black hole? This is what we will determine in this episode titled Lassoing Black Holes. Bill Gates, how are you doing today?
I'm doing fine, JFG.
All right, and joining us also is Peter, who has been challenging the theory last time. How are you doing, Peter?
Excellent, JF. I hope all is well.
All right, guys, it is my privilege as a host to start with my own pet obsessions. Today, as I was thinking about this episode, I started dunking photons in black holes just for fun, just shooting photons at a black hole. Gentlemen, give me an idea of whether that is a good thing to research. I've been looking at this basketball ring, and you know how sometimes we throw a ball and it doesn't quite enter into it, and it swings and it bounces, it rolls around the ring. Now it wants to enter, but it bounces out, it comes back in. Now here's the thing. I've been shooting photons at a black hole. And the same effect happens. If I shoot a photon here and it's of the correct wavelength, just the correct wavelength to be as big as the little circle here of the black hole, we get bouncing photons, don't we? And from that thinking, not only do I predict that some photons can pop out of a black hole randomly, I predict a prismatic effect whereby the more you get deep into the photon, the more the smaller wavelengths will be bouncing. And therefore, as you dive toward a black hole, I predict a separation of the colors of light such that as you enter it, it's all blue. And then when you're in, it's all red. Peter, what do you think?
Wow. Okay. So this is very interesting. You're competing here with Stephen Hawking, actually. So I guess you're in good company. Although Bill Gates, probably is not too happy with that, I suppose. But yeah, it's interesting. I would have to unpack that and chew on it for a bit.
Who knew that basketball would one day resolve the conflict between relativity and quantum physics? All right, so let's start with our subjects of today. Those were my little minderings of the day as I was eating foie gras with my girlfriend and just shooting photons on my piece of paper. Bill Gates, let's talk about the challenge that gravity poses at very high level to the rope theory of physics. Can you introduce us? Have you been thinking about it? And what is your take on how the ropes interact at the black hole level?
Well, I start at a different level altogether. I'm saying there's no such thing as a black hole. Black hole is a fantasy. It should be taken completely out of, it doesn't belong to physics. It doesn't belong to science. It belongs to religion 150%. The problem with the black hole, that's where we start. Problem with the black hole is that we have no idea. There's no mathematician on earth who can tell us what they mean when they say black hole. Black hole is taken to be, on one hand, an object, and on the other one, an abstract mathematical concept. And if you look at that, the first one, O2 black hole object that I sent you there, that one there. NASA says that that a black hole is a great amount of matter packed into a very small area. It's a sphere. They talk about tiny. They talk about small. They're referring to a little bowling ball, a black bowling ball or a black 8 ball. That's what they're talking about. Now, if you look at the next one, the O3 concept there, the next one, what is it? O3 black hole.
I'm trying to move to it. I'm just having a little trouble here. I'm going to get there. All right, okay. There it is.
Okay, and that one there, if you expand it a little bit, it says it's treated by all these people, especially if you look at the Max Planck one there, it says it's not a tangible object, it's a region of space-time or space or whatever, and they treat it as an abstract mathematical concept. So what's the problem? The problem is that half the world in math treats it as a physical object, a little ball. It says that star collapses or shrinks over time to the point where it gets to be a little ball, black ball, that's still floating in space out there. And the other half says, no, it's an abstract concept. This star completely disintegrated, became zero-dimensional. There's nothing there, and it becomes an opening in space-time to another universe. So first we got to determine, is a black hole a black ball, or is it a hole in space-time? Is it a region of space-time, a concept, or is it a standalone black ball? That's the first problem we got to resolve. And I'm saying there is no solution because they have never been able to define that, and they never will.
Well, to that, Peter, I tend to think that we all agree that a black hole is just a region of space that has extreme mass such that it is very highly gravitational. It is a point at which the gravitation force is enough to even swallow light, right?
I would say that certainly that is the concept, how it's normally defined. I mostly agree with actually in this case Bill's prognosticism or whatever it is
prognostic
of the situation here regarding black holes. If you saw the meme that I threw up there, I sort of give my 2 cents on black holes in general, where you have the problem where you have you cannot feasibly probe black holes at the lengths and time scales of the dynamic behavior that you're trying to explain at least at the moment. So so as a result, it remains a topic of mathematical speculation. So I would not consider this in the realm of physics as a result. It's often considered cosmology, perhaps, for example, and it's highly mathematical. So.
Well, I mean, I kind of disagree with you both here.
Black hole, Peter. Everybody out there believes they have been fed the story of the black hole, and there's not a single person out there that I can find that will tell you, "Oh no, black holes are speculative." Everybody takes it as a done deal. In fact, recently, what was it? About a year ago or so, 2 black holes collide, and they say, "Oh, we have proven not only that black holes exist, that was taken for granted, but the fact that it created gravity waves that reached the Earth, and they got a Nobel for it." And if you look at the Wikipedia or you look at almost any source, they talk about a black hole as a done deal. There's no fine print. It's a done deal. That's the problem.
I mean, perhaps I don't know all the details of. This is not black holes are not exactly my specialty. As I mentioned last time, my specialty is in foundations of quantum electrodynamics. Nonetheless, I would say that once you put a label on something, such as a black hole, it tends to stick in these fields, and that would be my response to that. I don't think we can really say, for example, that. It's as JF pointed out, we are pretty sure there's something quite massive that is pulling things in, and it probably is at the magnitude is quite large. To say that it's a singularity and to add all these other additional assumptions, I'm highly skeptical of it.
But this is a conceptual issue. This has nothing to do with looking through a telescope. It's got to do with what is a black hole, first of all. And second, is it possible, as you just said, that a runaway mass can pull on an object? Mass is a concept. I need to know the physical mechanism. In fact, I sent you folks there. Can you look at what is it? The fable of the elephant and the turtle? That'll explain it very well, I think.
So which number is that? Is that an illustration you wanted me?
Yeah, that's number, what is that? Let's see. That's 110 fable elephant turtle.
All right, there it is.
Let me go over that because that illustrates the problem completely.
The fable of the elephant. There we go. So what do we have to understand here?
Okay, here this is the fable. It says once there were 2 camps, right? There was a camp of mathematical physicists, and they were the elephants, and they did measurements and calculations, and they only respected one thing, and that was size. And among them was the biggest elephant possible. He weighed 30 tons. He was twice as big as any of the other elephants. And on the other side of the river, you've got a colony of turtles, right? And they were physicists. They were not mathematical physicists. They were physicists. And, they were slow, but they were very intelligent. And among them was, one of the persons that one of the turtles they respected the most. His name was Bill the Turtle. Okay, so Bill the Turtle had heard that the elephant, the number one elephant on the other side, his name was Dumbo. And since he was so big, everybody knew him as Jumbo Dumbo. Okay. And so the turtle crosses the river and goes to the other side and goes to talk to Jumbo Dumbo. And so what happens? Well, to make a long story short, he said, look, I heard, Dumbo, that you claim that you can affect things from a distance without touching them. And Dumbo says, yeah, exactly. You're right. And he says, well, how do you do it? Well, I do it through my mass. See, I have so much weight. I weigh 30 tons, and I can affect things from a distance just through my mass. And he says, that's so. Yeah, let me show you. And so Dumbo starts turning around. He spins. And the turtle, he starts orbiting around the elephant. And so he says, see how I'm doing that? He says, I'm doing it only through my mass. It turns out that what Dumbo did not understand or did not know was that the turtles had the ability to see in the ultraviolet range. They could see ultraviolet light. And so the turtle noticed real quick that what Dumbo had done is attach a stick to his shell, and he was twirling him around because of the stick. And so, and he could not convince all the other elephants that was the case because they couldn't see the stick. And so, to make a long story short, the story does have a happy ending, a very happy ending, because it turns out that, some poachers eventually shot Dumbo. They cut off his head and put it on their living room wall, and they chopped off his tusks, ground them into ivory dust, and sold it on the Chinese market as, fertility symbols or whatever.
And then the turtle exploded.
The moral of the story. But let me get the moral of the story. The moral of the story: never believe a Dumbo mathematical physicist, regardless of how jumbo he claims to be. All that comes out of the mouth of a Dumbo mathematical physicist is mumbo jumbo.
You guys are going so hard on the standard model. Normally, I'm the one who takes the edgy positions on this show, but I feel like now I need to stand for the standard model. When we say black holes exist, I don't mean that the singularity in the Einstein equation is a proper description of the inner functioning of a black hole. What we mean is that we've looked at these galaxies and these solar systems elsewhere, and we saw little stars spinning around a very massive thing that didn't emit light, and we can guess that this thing is so massive that it's what we call a black hole. We don't know everything that goes on into a black hole, but we know that there are these huge masses, often at the center of galaxies at least, and they tend to, there are stars just rotating around these things.
It's not true. Absolutely not. It has nothing to do with mass. It has nothing to do with mass. It's got nothing to do with runaway singularities, infinite mass. And, again, we need a mechanism. And mass is not a mechanism. Mass is a mathematical concept. You cannot say that I pull on you through mass. I can pull on you with a rope. I can pull on you with a chain, with some elongated object. I cannot pull on you with mass, even if I weigh like, Dumbo there. He's got runaway mass. He cannot pull on the turtle with mass. You got to explain the mechanism.
Bill,
the mechanism is the bending of space-time.
I do have an alternate mechanism, which I've sent you there. I have an alternate mechanism, a physical mechanism of this phenomenon you call black hole, and you can see it there.
Bill, can we agree that mass is at least a property of the objects we're talking about?
Absolutely not. Mass has nothing whatsoever to do with a phenomenon we attribute to black holes. I can show you if you put up there, what is it? 101 Cygnus X1.
101
Cygnus X1. 101 Cygnus X1.
Is it possible I don't have this because I have 111 Bird's Beak linear regime?
Yeah, but you have one before that, 101. You don't see that?
No.
Because what that's done is illustrate how they found the first black hole.
Okay, well, while I go to make sure that I downloaded everything from you, maybe we can answer the question. The problem is, do you recognize gravitation?
Of course, but we need to find out what gravity is, what physical object is causing gravitation. That's what we need to figure out. What's the invisible object that gets in touch with my pen when I let go of it and compels it to go to the center of the earth? That's what we need to identify. We have to make the invisible visible.
And you say that gravitation is not dependent on mass?
Absolutely. Well, it is dependent on mass. What I'm saying is the mechanism, the physical mechanism, has to have some elongated entity, some mediator. Why does a parachutist fall to the earth? Why doesn't he fall to the moon? Why doesn't he fall to the sky? Something is touching something is coming in physical contact with the parachutist.
And are you presuming? So, of course, there are mechanisms that predict this. There are theories, mathematical, artistic theories, I would say. Uh-huh. But this sounds a lot like the graviton, I would say. But perhaps you're alluding to the rope.
I'm alluding to the rope, of course, because the graviton is a particle, and I cannot pull with particles. That's the problem. Mathematical physics does everything with particles, and there are no such thing as particles. You cannot produce any phenomenon of nature. You cannot explain any phenomenon of nature. You cannot simulate any with particles.
All right. Well, I would say when we get to it, I think JF's trying to pull something up, but later on I have a video to show that particles. It's really hard to deny the existence of particles, but we'll get to that.
All right. So, Bill, what I'm missing in terms of pictures, I didn't get an email with everything from 101 to 106.
You didn't? Okay. Well, we can do with that. If you look at Cygnus, look at 106. Cygnus X.
I'm missing everything between 101 and 106. I have 107. If you want to take the time to send them to me, maybe you can take that time.
Okay, let me see if I can, give me a second.
And while you do that, I will be reading one of the reactions of the crowd while you do that.
Okay,
Fizziz sends 10 euros. He says, what substance are ropes made of? And how can you prove it and observe it? Don't try to deflect the question with bullshit about how you don't need to prove it. So we will let Bill Gates get his pictures in order, and then we'll get back to that question. But Peter, I wanted to ask you about what was my conclusion. The first time I talked with Bill Gates, it is my impression that there could be such a thing that resemble rope properties in the building of the universe, in the way quantum fields are intermingled with each other. And there could actually be rope-like behavior in the way a photon just advances linearly through a 3D space. But I feel that quantum field theory provides this theoretical framework whereby you could have little fields that sometimes they behave more electrically, sometimes they behave more magnetically, and it does look like a rope when a photon advances through these fields. Would you agree?
I agree with most of what you said. There are certainly many analogs, and it does predict quite a bit of what we do observe, or you can use something like that Bill Gates has to describe the same types of physics. And there's nothing wrong with that. Describing the field theory instead of using something like oscillating particles, which is what we do now. Twisting ropes, sort of like a rotary dynamics sort of model. It's interesting. I would disagree with your point about light moving in straight lines, though. At the quantum level, we have, that was one of the papers that I sent to Bill. I don't know if you had gotten that bunch, the first debate.
Yes, I got your bunch.
Well, I don't know if Bill, if JF did, but we do have evidence that light does not move in trajectories that are strictly straight lines.
Oh, so how does it move? I'm curious about this.
So I guess one would need to go back to Feynman's path integral formulation of quantum mechanics. That is one way to describe it. So you can describe light as moving from point A to point B along a series of different paths simultaneously. It's not just, and you can restrict the particular paths that it might go. That is why when you have, say, your double slit experiment, you shine light on your double slit, you'll see a constructive interference peak right behind the slit. Your 0th order peak will be bent around your slit. That you can't explain that with straight line paths.
Very interesting.
Only.
And one other thing, while Bill Gates is actually succeeding at sending me his pictures, so we'll get back to the discussion. But one other thing I was curious about is time. How does quantum physics touch time? Is that a dimension? Is that a property of the things? How do we conceive of time in quantum physics?
Yes, it is it's a parameter treated just like you do in classical physics. It's a coordinate system like space and time. Now, how you might interpret that is varies from person to person, but it is just a coordinate as spaces, but it has a special property that at least in some systems, it's irreversible. It's not something that you can, in most cases, go backwards in time as you can go backwards in space.
All right. So, Bill,
I tried to go backwards in time, but I'm still 66. It doesn't happen. I don't know. I can't get the Earth to go in the other direction.
All right. So, Bill, before the interruption, what did we want to talk about? We had the 101 Cygnus,
Okay, the 101 Cygnus, what it does is show you how they supposedly discovered or proved black holes, and that is what you mentioned earlier, a star rolling around nothing. In other words, going around in circles or orbiting a center in which there is nothing.
You're telling me I was deceived by this YouTube video showing this orbit?
Bill,
I don't see it. I don't see the orbit.
Oh, sorry, I'm not. Am I showing it? There it is.
Your screen's up. There you go.
There it is.
Okay, so this is how they discovered. They went in there and they saw HD 226868, which is Cygnus X1, and they saw that this star was rolling around nothing. It was going to simplify it, it's orbiting around nothing. Okay, so that's how they came up with that one, right? And they said, okay, there must be a mass, and they put that mass, that black hole there by hand. They just inserted that, say it's got to be mass. What else could it be? That was their conclusion. Okay, and then you can jump to what is it, 106.
All right.
The Cygnus X1 rope model. This is the rope model. I'm saying this is not done with mass. It's done with magnetism. It's a magnetic field of the entire galaxy that is moving the star around. Remember, a star is a charged object. Okay, so all stars are charged. All stars have magnetic fields. And if you look at number 105, ball and magnetic field.
Do stars tend to be charged negatively or positively?
Well,
they're charged neutral.
They're charged. Remember, it's got a magnetic field. I'm talking about the magnetic field of a star. Now, if you look at that there, you can see what happens here on Earth. We can do this in the lab. You take a charged ball, and you put it in a magnetic field, it'll spiral around. That's a black hole right there. That's what's happening. What you have is the magnetic field of the entire galaxy swooping down on a star and forcing it to spiral around nothing. There is no mass in the center of that orbit.
You have got to be kidding me, Bill Gates. You're telling me that the whole dark matter thing is like an adjustment that scientists have been doing, but that none of it relies on gravity. It's all a big magnet system?
Okay, let me show you another bit of evidence. I don't like to do evidence, but here I'll give you evidence. Okay, look at the last one there. Where is it? Well, no, it's the same one. Cygnus. No, it's the, what is it? Which one is it? The 103 spider web. 103 spider web.
So there it is.
Okay, I'm saying that all stars are interconnected. They have to be if every atom in the universe is interconnected by the ropes. So we have electromagnetic ropes binding any two atoms in the universe. That means that all stars are made out of atoms. They're connected to all other stars. Think of it as a spider web that is superimposed upon the galaxy. So now we can see why the stars on the edge of the galaxy rotate just as fast or faster than the ones on the inside, first of all, and why a galaxy rotates as a single platform. It rotates like a bicycle wheel, in other words. That's why, the problem with the galaxy rotation problem that they cannot solve is how is it that the stars on the outside go faster than the ones on the inside? And you can see that in the curve. If you look at the curve there, it pretty much explains what the mathematicians are looking at. It's, which one is it? It's number 06 dark matter graph. 06 dark matter graph. You can see what happens there. If you look at the curve, it disappeared.
There it is. I think we're seeing it, right?
You can see the curve. The bottom curve is what is predicted by Newton and Einstein's equations. Instead, what they observe is that the stars on the outside have a greater speed than the ones on the inside. And they cannot explain that. And what they did was, if you look at now 109 dark kilograms, 109 dark kilograms.
There it is.
What they did is they put kilograms mass to cover the hole. They said, look, there's this dark matter that we cannot see. It's invisible, but it weighs a lot. Just like the black hole. They're all conveniently invisible. They all weigh a lot, right? And they just put it in there. Why? Because the mathematicians deal only with mass. That's the only thing that came to their mind that could produce this effect. And instead, if we interconnect every atom, if we can interconnect every star, we can see why the whole galaxy rotates as a single platform. We don't need to put this false mass in there, these kilograms, because that doesn't even explain why or what keeps one star attached to another star. If I put all this mass in there, what am I doing? I'm just artificially producing this effect by saying, okay, in my equation, I'm going to be putting all this mass at different levels to produce this effect. That's the only way they can do it. But then they have to put the spirit called dark matter, just like a spirit black hole, because they all want to explain it with mass.
This is fascinating. Peter, what do you think about this? I'm still under shock of having to divorce from dark matter. I was attached to my little pot of dark matter.
Well, let's try to unpack a little bit of this. And Bill is very good at throwing quite a bit at us, but I really appreciate it. Now, when it comes to these magnetic fields that are spiraling these massive objects like a charged particle, if it is a magnetic field or whatever, a similar mechanism that we call a magnetic field, I think we're discussing the same thing. Why, on a small scale, do you have positive and negative charged particles they will spiral in opposite directions in a magnetic field. Whereas on this larger scale, you do not have such a dualistic effect where you have spinning clockwise and counterclockwise based on something like charge. Why wouldn't that occur on macroscopic scale?
Well, keep in mind that, again, a star has a magnetic field, and we're talking about a little tiny in comparison to the galaxy. A little star has a magnetic field, and what I'm saying, that magnetic field is within a bigger, a gigantic magnetic field, and it's that field that's moving that little star around. It's affecting that star.
Sure, but why?
So we don't need the electricity. See, you're referring to electricity right now. You're saying a charged object. When I'm saying that a star is a charged object, I'm referring to the fact that it's got a magnetic field, and that magnetic field can be affected by the galactic magnetic field.
Right. But imagine if that magnetic field of that star was, say, they're not all going to be all. Are you suggesting that all the stars have the magnetic field pointing in the same direction? The only way that your model might work, and I'm not even convinced that it would, at least in terms of how we define magnetic fields, would be if all the magnetic fields were aligned, then you can have the majority, if not all of the stars spinning in the same direction. If you have, say, 50% of the stars having their magnetic field spinning flipped, then you would have a mess of rotation. Well,
if you take a magnet, all the again, you got to look at what a magnetic field is, and it's the flow of threads. If you look at, let me just show this, and it'll probably put it into perspective. I'm saying that what is a magnetic field? Can you look at 104 magnet in water?
All right, there it is.
Okay, if you put a magnet in water, and you, in other words, if you sprinkle iron filings at random in water, and then suddenly you put a magnet, which is what they've done here, you can see that the iron filings are collected one by one. See, it's gradual. It's not like, they're when we do it in dry, when we throw iron filings, sprinkle it over a magnet, they're all there, they're all static, and you say, okay, yeah. But here you can see how the magnet is collecting them gradually, one by one. Yeah. And my point is, there is matter, like James Maxwell said, a magnetic field has matter in motion. There's some kind of exotic matter in motion. What I'm saying, those are the threads. Right. And the threads are oriented in such a way that they force every one of the iron filings to also align along the magnetic field. So you were right the first time when you were talking about the stars. If the galactic magnetic field is just a bunch of threads, gazillions of threads sweeping around the inside, the center of the galaxy, and out the edges, it's going to align every star in the same direction.
So, therefore, you would predict then that
I don't predict.
Okay. However you have to use.
Careful. There are such a number of words we cannot use with Bill.
I don't want that word prediction because that's astrology.
Your claim is that all of the poles, all the north and the south poles are all aligned of the different stars in the galaxy. That's the only way it works. So
I would think that's the case because, again, you have to remember that that's what a magnet does. It aligns everything in the north-south direction.
Okay. So now if I throw charged particles at stars, okay, and it will have the same effect, or some large, massive charged, not a particle, but a massively charged object, say say the north part of this star, you will be able to detect which way the stars are spinning, are aligned. And
my best guess again.
I'm highly skeptical of this.
I can provide a mechanism and say I need a physical mechanism. I don't want to go in there and say I can describe it, with an equation. That's not physics. That's mathematics. I'm saying I need a physical mechanism. I got to show how it is that I incorporate the black hole together with the galactic magnetic field in this case, or the black hole phenomenon together with the galactic magnetic field. And I'm saying, yeah, you can do it with threads. You don't need mass.
Do we have a way to know the north and south orientation of any star that's far from us?
I don't know.
No. Wow.
It's
as far as I know.
You need a probe. So if you have, say, if you have identifiable objects that are, say, charged, that are moving near this magnetic field, then you'll know which way it will deflect, and then it can. So you could send a charged probe towards these stars. Now it takes a long time to do that, and I don't think we actually know some of these massive objects. It's not easy. I could be wrong, but I don't think you can easily detect at the moment.
Here's how we could resolve.
Let me give you a little clue, Peter, because they may be able to determine this in this way. You keep in mind that they've discovered these jets coming out of the center of galaxies. They call them jets, and they think it's a black hole, a massive black hole in there that is spitting out material like a geyser. Okay, that's what they're saying. Okay, and let's assume that's true. Let's assume that we have some object, maybe a star or something, and it's observed coming out of the center of the galaxy because it's being pushed by something. Well, then you know that that's the north side of that galaxy because it's pushing it outwards and coming, from the bottom up in that sense. Okay.
So we would know this is north charged.
And the spouting part would be the north pole.
But here's the problem with that. Oh, I'm sorry. Go ahead.
No, I mean, I was just saying then we would use this matter. We would have to see it, get to some star, and then we would know those stars' orientation.
Yeah, but JF, the problem with this is the time scales. In order to space the time scales to do this experiment are absurd. It's frankly not going to happen.
Now, you can go ahead, but then I just wanted to say, Peter, there could be, within the formation of galaxy, a mechanism that aligns the stars. Maybe at the beginning, they were not all aligned, but by shaking some magnetic field, by some sort of inversion, you could end up with all the stars relatively aligned to a single direction.
Here's one of the problems, is that magnetic fields magnetic forces or magnetic fields, however you like to put it, are not very well long-range interactions as far as we can measure on the small scale. They don't. So in order to push something to get them all aligned on such from at large distances, they would need to be the galaxies would need to form very close, all the stars close together for what you're describing to happen. That's why you have like a magnet, you can get all the different poles inside the dipoles inside of magnets all aligned because they're all very close together. It works out. Gravity.
But you do agree that a galaxy has a galactic magnetic field.
I would not say that yes, I would say that there are charged moving particles, and there is what we call a magnetic field. I prefer potentials. I prefer potentials, as I said last time, but the electromagnetic potential.
I'm saying, does a galaxy have a magnetic field? It's a yes or no question.
It's not the drawing. If we drew the field lines, it would not look. I don't think it would look like the way you're. I'm quite certain it would not look the way that you've drawn.
Why not?
You've drawn it.
Why not?
For one, the field lines aren't aligned the way they are. I don't. Unless you reinterpret the way magnetism works on large scales, which we don't see with when we put magnets together, it does not have such a strong strength far apart. It just doesn't work.
Okay, let me ask you: the sun's magnetic field, does it extend beyond Pluto?
Weakly.
Does it? It's a yes or
does.
No.
Very faintly. It does.
How far does it reach?
It
reaches all the way to interstellar space, way beyond.
Sure,
way
but
beyond
it's very
Pluto.
weak.
So now the question is, does a galactic magnetic field, where does that one extend to? Does it extend to the last star or beyond?
It's kind of like asking the butterfly in Africa that is flapping its wings. Does the wind influence that? Is that blowing my cheek right now? I guess you can say yes, it does extend that far, but don't need to put up a windshield for that at the moment.
Well, I don't know. I'm saying that the galactic magnetic field extends far beyond the last star in the galaxy.
All right. Peter, did you have something to add?
That's how big a galactic magnetic field is.
Yeah, I mean it is that far, but it's not sufficiently strong. That's all I have to say about it.
Yeah, it doesn't have to be really that strong.
Keep
in mind that we don't need. I agree with you. It's not strong out there. It's strong near the
not strong
center.
enough for what you're describing. What you're predicting. It's not strong enough to
strong
influence.
Enough for strong enough for what? What am I predicting? What do you
for things like magnetic field alignments of these stars?
Well, it's like saying that the iron filings that go around the magnet are not affected by the magnet. Of course, there's a range. After that, if you pour more and more iron filings,
right,
at some point the magnetic field is not going to reach it.
No, it's more like two magnets too far, very far apart. You're not going to very close. One's going to flip as a response to the other. But if I send the magnet very far, one's not going to flip as a response to the other.
Right, and I agree. All I'm saying is that the magnetic field extends way beyond.
Sure.
Now, I'm not saying that it's strong out there. Where it is strong, that it's where it can produce the black hole phenomenon. That's where it can twirl a star around.
But the magnitude matters. I know you don't like mathematics, but the magnitude, the numbers,
no, I agree.
the strength matters.
Of course, I do agree with. Of course,
in order to say that your model works, it matters.
Now, Bill,
but my model works. What?
In order for it to work, the mathematics matters.
Yeah, of course. You have to describe it mathematically. I don't disagree.
You've made a stunning case to me that, okay, I could detach myself from the idea that mass is causing all this, then I would go for magnets. But then there needs to be a whole lot of rope to generate the kind of magnetic field you're talking about. And as we've seen in the Jussie Smollett case, any action that requires a rope leads to some guy having to go buy the rope. And we should have cameras of people buying that much rope at the middle of the galaxy. How do you get that many ropes at the center of your galaxy if it's not mass?
There's a quote from Richard Feynman. He was a 1965 Nobel Prize in mathematical physics, and he said that there was a ratio between the magnetic field and the gravitational field, and it's a ratio of 10 to the 47. And he says, where does such an enormous number come from? Well, now we know how many threads or how many ropes there are in at least in our galaxy. Maybe there's more. But my point is,
saying magnetic
how many atoms are there in a galaxy? How many atoms are there in a star? So you're talking about gazillions and gazillions of ropes, of threads. Those form the magnetic field.
Oh, so it's not so much that there's something at the middle. It's the combined effect of all the atoms in the galaxy that generate this field?
Every star generates a field that extends way beyond the planets, like in our case, the solar system. The magnetic field of the sun extends way beyond Pluto. And just imagine now every star with that. Every star has a magnetic field. It contributes to the magnetic field of the galaxy because the magnetic field of the galaxy originates in the magnetic fields of the stars. And so all these threads are going up the center of the galaxy, coming on the outside, and they help maintain the integrity of the entire galaxy, while meanwhile all the stars are interconnected to each other, and the whole thing rotates like a carousel. That's my proposal.
Peter, what do you think about this? It sounds to me like Bill is suggesting a kind of self-organizing principle whereby originally decoordinated magnetic field could coordinate and could naturally kind of emerge into a spiral of aligned structures.
Well, I'm highly skeptical that these what we call magnetic fields can sufficiently describe what Bill is doing is trying to describe. Now, if on the other hand there was a separate type of rope, there was gravitational rope and magnetic rope, where the strengths are different, where the number of ropes differ, so that there's maybe more different types of rope that are connecting, for example, my two balls. I have not only my electric rope and my magnetic rope, but then my gravitational ropes, for example, and they tug at different strengths. Then I might be on board.
But that's not the model. That's not my model is if you twist those two around, you get one rope. The blue and the red are threads. Okay, the blue and the red are threads. The rope is what the threads do when they're twined around. What I'm saying is the magnetic field is composed of threads, not of ropes, but of threads. Right. So it's the threads that are going around because they're swung around when you have a row of aligned atoms. They are merged. The whole line swings around and they swing the threads around. That's a magnetic field. It's the swinging of countless threads around a row of aligned atoms. That's what we're going to call a field.
And so, if, for people who will remember our past episode, essentially the magnetic field is one of the thread, the magnetic one, right? That is being swung like a children just in a school, just swinging a rope around his body. That's it. And the red stays in the line of atoms.
My son corrected me. I like his idea better. He said both threads swing around. One swings,
both threads?
Up, the other one around. So they're both swinging around. And I think that's a better model than the model I originally had in mind, which was that one of the threads comes out. I think both threads really swing around, and the magnetic field is composed of both.
But based on the question from Peter, isn't that a problem that matter seems to display effects that are both magnetic in nature and gravitational in nature, given that in your model, the same rope or the same threads are operating these two effects? How do you deal with the combined effects that are sometimes gravitational, sometimes magnetic, when they both happen to the same atom?
Well, that's when you have a magnetic field, the rope now disassociates itself. In other words, it doesn't break it. It just the threads come out, they start swinging around, but then because the threads are swinging around, they're pushing outwards. That still maintains the tug between two atoms that are part of that magnetic field. There's no gravity in the sense of, a rope connecting them, but the fact that the two threads are pulling outwards during the spinning of the two threads, that already maintains the integrity of those two atoms together. In other words, they don't fly apart because of that.
Well, let's say I have two atoms in a magnet. Are they gravitationally attracted to each other? Or are you saying that what keeps them together is totally different from what brings the moon to the sun or the moon to the earth?
Well, in that case, I'm saying that if you have two atoms that are interconnected by a rope, and the rope now starts, the two threads come apart and they start swinging around, that maintains the tug between those two atoms. Why would they fly apart? I mean, why would they?
Well, Bill, you got
the model there, Peter. Show us the model one more time, please.
Sure. Well, Bill, I'm joining in your.
Let me explain that. If you pull them apart, if you pull the two threads apart, do the balls go flying outwards? No. Right.
If I cut the rope, then I will. Then I will. But yeah.
I'm not cutting the rope. I'm saying if you pull on the two threads, the balls don't fly apart. That's what.
So they are still attached through a limited length of the cords. It's just that the cord is in a different configuration around the atoms.
Right, because what I'm saying is the threads are now spinning, and because they're spinning, that already keeps the two atoms close together. It's not like the two atoms now can fly apart.
Right.
Now,
So,
go ahead, Peter.
So I have joined indeed Bill's, and I wouldn't call what he's doing necessarily physics. I would call it topological art, and that's we're using geometry without a metric. So it's topology, and we're really playing with art here. He makes fantastic videos. It's just a kind of a jab there. But yes,
I like your model. Send it to me. I'll buy it from you.
No, will do. It's a high price, but sure.
So, Bill, my question is, how do we get these swinging ropes? I guess my question would be, what is the difference between magnetic matter that generates a field, and matter that doesn't generate? What gets it rolling with the ropes, and what gets the rope detached and starting to generate a magnetic field?
Well, you get a stimulus. Again, what happens is we have to understand electricity. Unfortunately, I didn't know you were going to ask that question. Otherwise, I would have sent you a little GIF there. But this is, let's see if I can explain it. What is voltage? These people don't know what a voltage is. They always explain it through analogy. They say, look, if you get a high spot here in the river, flows to the lower side because there's a difference in potential. That's all they tell you. And you haven't understood squat because all they did was give you an analogy of, maybe a river or something like that. And I'm saying what it is very simple. Voltage means clockwise and counterclockwise. That's all that Mother Nature understands. So if you have a row of atoms, right? From my end, they turn clockwise. From your end, they turn counterclockwise, even if you turn the row in a curve. Like if you have a wire, right? You have electricity flowing through that wire. What is it? From my end, from my starting point, they're going clockwise. Hopefully, by the time you get to the other end, they're going counterclockwise. And that's what voltage is. Okay, so voltage is simply a spinning clockwise or counterclockwise of a row of merged shells, electron shells. Okay, so all these atoms are interconnected, and that's what electricity is.
All right.
So,
Peter.
Bill,
Yeah.
Bill, I would say to use your model.
Yeah.
If you want to define what voltage is a voltage is if, say, you're using two electrons. It is a measure of the stored potential energy of the system, and what we would mean by that would be the measurement of the number of twirls or spins in the particular rope. I think that would be a little bit more accurate. Counterclockwise would be, say, positive, and then clockwise would be negative. Would you agree with that?
Voltage has nothing to do with a rope. Voltage is atoms. Electricity is atoms. In other words, you have to have merged shells. All atoms are merged. The shells, the electron shells, the outer shell merges with the guy next to it. You have a row of merged shells, and they're all spinning in the same direction. That's electricity. Voltage is whether from one end it's going to be clockwise, the other one end it's going to be counterclockwise. It's not the rope. The rope does light. It's atoms that do electricity and voltage.
I would say that no, the voltage we're talking about, the lights that we talk about, light is an oscillation. It's a wave of the voltage or the electromagnetic voltage.
Yeah, it's a wave, whatever wave is.
But it's not the atoms.
Wave is a concept. We can't use the word wave in physics. Wave is
of the rope. It's a wave. It would be a wave of your rope. It would be, say, you have a traveling
torsion.
But it wouldn't be your atoms. If these are your atoms and then this is your rope, they would be distinct objects, I would say.
Yeah, what I'm saying is if you put the model again, the two balls are connected. If you touch the two balls there. Just touch them. That's electricity. They're both spinning in the same direction from your left hand, from one hand to the other. They're spinning in clockwise, for example, both of them. Like
okay.
That. So from one end, it's clockwise. From the other end, it's got to be counterclockwise. and that's voltage. I'm saying that it's merged shells. A row of merged shells is electricity. And voltage is simply a stimulus that you give to that row of merged shells.
Now, Bill, given that you are talking about merged cells, what about the valence electrons? The fact that copper and gold are good at transmitting electricity, it does seem like it confirms some sort of a electron-based theory of physics. How do you explain it from the perspective of the ropes? Are they just matters that are more easy to merge?
Well, keep in mind that, what is the molecular orbital theory? They don't use the electron at all. They throw the electron bead away. They throw it in the trash can. They forget about that, and they start dealing with what? With orbitals. What the hell is an orbital? There's no such monster as an orbital. An orbital is a balloon. You can merge balloons, but you cannot merge trajectories of electron beads, which is what they're doing. They're saying, look, an orbital is just a region, which is a concept, not a solid object. It's a region where you can find the electron bead. Then they get rid of the bead and they say, now let's merge the shells. Let's merge the orbitals. And I'm saying those orbitals that they've been talking about for 100 years are actual shells that are weaved by the threads. And when two shells merge, now we can have this molecular orbital theory with objects, not with abstract concepts like, orbitals. There's no such thing as an orbital. Orbital is just a way of saying, look, we're not going to get rid of the bead, but we can't explain, molecular orbital theory with the bead. So let's get rid of the bead. Let's do it with the orbitals.
Well, that's a critique of the standard model, but you still don't have an explanation. Why is copper so good and gold so good at transmitting electricity?
Well, we would have to look at the specific case. I can't, off the top of my head, just tell you right now, this. Answer to that question. I would have to look at the specific case.
You bring up an interesting point, JF. I mean, the only small minutia, I don't mean to be what you'd like to call autistic about it, though that's not really autism, just trying to make sure they use the words correctly. It would be conducting electrons, not extra valence electrons, but that's neither here nor there.
Yeah, that's true.
Why would the electrons be moving from one atom to another? Why would the electron bead go from one atom to another?
Well, why do molecules of water in a river, why do they get pushed down the river?
Yeah, but listen, we're talking about an electron bead. What compels a bead to jump from one atom to another?
Because there's more bead on this side and there's less beads on the other side, Bill.
And that doesn't mean that the bead is going to go there. Absolutely not. That's magic. That's doing it with spirits. What you're saying is a bead just moves for no reason. Nothing touches it. Nothing comes in contact with the bead, but the bead simply jumps to another atom. Why would that happen?
Because the beads are self-rejecting. Because one bead is electrically negative, the other bead is electrically negative. It will naturally flow toward where there's no bead, because the magnetism will push the beads, the negative beads, away from themselves.
There's no such thing as negative or positive in physics. That's also a mathematical concept. That's like saying, look, we're just going to name this one X, the other one a Y. X moves this way because of God, and the Y moves that way because of spirits. That's all you're saying. There's no reason for a positive bead to go anywhere unless something comes in physical contact with the bead.
The physical thing that comes into contact is the intermediate photon, or the intermediate light particle that interacts between, say, two electrons. Now you call that rope, but that is the mediator. So it is like a game. You're
going to do this with particles. You're saying that we have a bead and we have another bead, a particle you call a photon, and how does this bead? So we're just shooting it, right? One is shooting a bead to the other one.
It's like, so Brian Greene has a great analogy on this. Imagine that you have two, a father and a son, and they are two electrons, okay? And they both have, they're playing baseball, right? And they're throwing a photon, which is the ball, at each back and forth between each other. That's the photon, and there's a recoil force that pushes them when it strikes their mitt. There's a recoil force that pushes them back. This is what is the mechanism how we, if you want to be descriptive, to describe how the photon pushes the two electrons apart, and the same type of mechanism would be used to describe the interaction between electrons and nuclei.
Okay, now using that same mechanism, right? Let's see if you can continue, because that's where quantum falls completely on its butt. Explain pull now. Tell me how a quark pulls on another, throwing a gluon bead at it.
A gluon, or do we talking about? Can we keep with photons?
What is the mediator between quarks? Isn't it the gluon?
Well, how about? Yes, you're right in that we have not sufficiently described.
You never will with particles.
I'm not. But how about a nuclei? So a nuclei and an electron in terms of a pull. We don't need to go to quarks. So we can talk about, say, a nuclei, which is a bunch of protons and neutrons. But so something positively charged and an electron. We don't need to talk about quarks in that.
I don't understand positive. That's not a word of physics. It's a word of religion.
The proton. My apologies, Bill. The proton, the nucleus, the bundle of particles of protons and neutrons is the nuclei, and yes, the glove would be different for interaction would be different for a positive charge versus a negative charge, and it would depend back on your polar. This is more difficult, but yes, I admit. But somehow the glove gets sucks back in, which is unphysical, at least on our scale, but does not mean that it's not physical on the smaller scale. If you humans cannot conceptualize. Fair enough.
Okay? Forget about we cannot conceptualize pull mediated by particles. We cannot explain gravity, and we cannot explain how a quark pulls on another quark with particles. Period.
Bill, I'm going to make it very easy here, because you don't like bringing the proton and the fact that it's positively charged. Two freaking magnets. They pull each other.
Yes. How do they do it? How does a magnet pull on another one with particles?
I have no clue. I would have to have Feynman. Feynman, help me, Feynman.
You never will. With particles, you can never do it. You would have to introduce magic in there. The only way you can do it is like I'm saying. The threads are going around. They latch onto to each other. Now you can pull. Yes. But you can't do it with particles. Never. That's why we don't have an explanation to this day of how a magnet attracts another. Because, you can't do it with particles. You can't do it with quantum.
Hey, Bill, I have a question. This is a more. I find this to be more of a communication style issue more than something about physics.
It's a conceptual.
Why? So using reasoning for say real world interpretive in reasoning as opposed to understanding abstractions.
Well, abstractions is magic. If you
why is it magic?
You cannot conceptualialize it. It's magic because if someone says a positive particle attracts a negative particle, he's introducing spirits. He hasn't said anything.
Bill, it sounds like that you cannot conceptualize it.
No, I want you to conceptualize it for me. How does positive attract negative? What does positive mean physically?
So physically, in terms of if I go to the hardware store and ask for something positive, is what you're asking for?
I'm saying you just gave an example of father throwing a ball to son, right?
Right.
I want you to conceptualize for me how father throws a ball to son and pulls on him. That's what I want someone to conceptualize for me. It's a conceptual issue.
So here would be one. Okay, instead of now the son, instead of having a mitt, he has a tube. Okay, a tube where the ball comes in, it gets looped around, and then
elongated object, right?
And a twisted object,
elongated object. Let's clarify.
A curved object.
Yeah, but it's an elongated one that connects one to the other.
No. The boy is holding it. The boy is holding, say, this tube.
Yeah, but it's an elongated object.
Curves around.
It's an elongated object between your two hands. That's my point.
No. I'm the boy, and you're the father. You throw the ball to me. The ball comes into my tube. It twirls around, and then instead of a mitt, it twirls around in the tube and gets and pushes when it hits the end of the tube, and then pulls me towards you.
Why would it pull towards you? It's the tube that's pulling.
Because the photon in this case would pull me towards you. Bill,
why would it pull you? Why? Because of the tube.
I might need a drawing for this better than
why did you introduce the tube? That's my question. Why did you put a tube?
So that it could twirl. So that
but you need an elongated object called a tube.
But it doesn't need to extend. It doesn't need to extend from one from me to you. I can hold on to the tube.
Can I pull on you with a curved ball?
Can you throw at me a curved ball? No.
Pull on you. Can I pull on you with a curved ball?
Yes, if you allow the Einstein bending of the universe, there could be a curve that goes back and pushes you back in. A wormhole curved ball, that would work. No, but I mean, this is a fundamental thing that every time I discuss with Bill, we end on this. Bill rejects the idea of pulling, essentially. He says there is only one way to move object. It is to push them. And you can have a rope, of course, which will give you the impression that you're pulling. But what you're really doing is you are pulling on the rope, which is pushing on something, which is your grip on the rope. I don't know what to say about this, Peter.
Well, I mean, because he's forcing his hand in terms of the interpretation being a physical interpretation in something that we understand classically. That's the catch. I mean, but there are physical mechanisms that I'm trying to it's a bit silly, but you can illustrate. For example, you could have a mechanism where, say, your ball enters the boy is holding this tube where the ball enters the tube and then comes around and then hits the end of the tube. And then once it slaps the end, it pushes him in this direction towards the father, which is on the other side. I digress.
So you're producing pull by push.
Yes.
So you cannot produce pull in the religion of quantum mechanics, no matter how you do it. Is that correct? You cannot produce pull.
I didn't say that.
Donkey, like straight ahead. You cannot produce it. You have to go through this push mechanism, this Casimir effect type mechanism where you remove particles or where you push the guys together. That's the only way you produce pull.
To be honest, Bill, this is actually something that I ascribe to. I'm glad you brought up the Casimir effect. The Casimir effect. So for people who don't understand, to explain, you have, say, two charged neutral plates, and then you have a photon that is not just bouncing back and forth between the plates, but it is there is an elongated photon in Bill's term. There are normal modes of photons that interact inside this plate as opposed to outside. There are more modes of the photon, like sort of harmonics outside, versus the restricted modes inside the mode. And as a result, they come together. So so this is actually quite natural. You can imagine, for example, two electrons or two positively charged particles in Bill's, as in Bill's example, where the photon is everywhere along the between the two particles. This is a strength that I think might have some veracity. Now, I should mention that up until now, but say between two electrons, we have not observed the Casimir effect, and there is quite a bit of experimental speculation in terms of even the Casimir effect that we've measured with metal. Have we actually seen it?
all I can say is comment the following. The reason quantum mechanics has never discovered the graviton and never will is that you cannot produce gravity with particles. Period. We're done. And they never will. They cannot conceptualize. They cannot conceptualize how a pen falls to the floor with particles. What is the earth throwing? Particles at the pen? I mean, how is it done? It's very simple. The pen has to be connected, physically connected to the center of the earth. Then we can explain it. We can explain it with ropes. We cannot explain it with particles. And we never will. That's why quantum, 100 years later, cannot explain gravity.
Maybe. I'm not. I don't think. I'm not. There are a lot of Of course, there is a lot of issues with gravity. I won't deny it. I'm not in the field of gravity. I should mention, by the way, that we have not even observed for small particles. We've never even measured the gravitational effects on most of these particles. It's a very difficult thing to do. We've never. So it's hopeless to some degree, in part because we haven't even measured yet if the electron falls.
But hold it, Peter. I'm not talking about the invisible subatomic world. I'm talking about just the regular, everyday world in which we live.
No, you said quantum.
No. Forget about quantum for a second. I'm saying general relativity explains the cosmic world. Here on Earth, we have to explain the falling of a pen to the table. We have to explain it in regular terms. How does a pen fall to the table? I mean, here we're talking about this distance. What is it from here to the table? How do we explain that simple thing? How do you explain with particles? You cannot. You never will. And that's the problem with quantum. Quantum dies with gravity.
What's your position on this, Peter? Will there be a graviton detected, or do you think that quantum physics will just get eaten by relativity and eventually by rope theory?
I would say that Bill is jumping the gun to some degree because the problem with his framing is that if we're talking about the pen falling, we don't even have a complete. Even if you take aside the gravitational effects of this pen, we are still working on completing the full theory of how this pen operates by itself, macroscopically.
How can it be, Peter? I mean, we're talking about a pen and a table. That's the entire system. Why can't a mathematician on Earth just explain to me how this pen falls to the table? That should be very simple.
In terms of particles, I mean, you're talking about on the. Are you asking from a quantum point of view? What's point of view are you asking it from?
How would quantum explain this simple phenomenon?
So it's kind of like asking a biologist use cells. No, use the organelles to describe why. When I chew potatoes, it tastes. No, that's not even good. Why? Some people like. Oh, okay. I think it's there's too far in terms of scales to even describe it accurately.
But Peter, a science of physics should be able to explain how the pen falls. That's a simple thing. It should be able to explain it.
This is very simple. And here we are, 2,000 years later, not a single mathematician on Earth from Harvard or from Cambridge can explain how a pen falls to the table. They cannot explain that simple phenomenon. That's ridiculous because this is the simplest. All we have is a pen and a table. That's the entire system. If someone cannot explain that, something is terribly wrong.
Maybe.
But with ropes, every atom is connected to the table. Very simple thing. We're done.
But we can use a quantum theory of your ropes if we, as I said, with the Kashmir effect. I had forgotten to bring that up last time. But yes, if you the field which is describing the rope or the particles moving around between macroscopic objects, you can have some sort of effective fall. But it's I'm not an I personally cannot explain it. I'm not sure. I've never looked for in the literature how does the pen fall. So I'm out of my wheelhouse here.
That's for the next JFG presentation.
All right, guys, I have to leave for 1 minute, but Peter, I wanted you to explain to our crowd. Are you familiar with the with quantized inertia? People are asking questions about this. Are you familiar with the concept quantized inertia?
I am not. Would you like me to look it up while you're during the 1 minute break?
In any case, you guys can discuss anything you want. I'll be back in a minute. Bill, I don't know if you had something to add, or Peter. And Peter, you can Google quantized inertia. I'll be back in maybe 30 seconds.
Okay, quantized inertia. Let's see what that is. They invent new concepts instead of simplifying. We make it complicated. Quantized.
Fringe theory. Okay.
It's a fringe theory.
Wow.
Yeah. All right, guys, I'm sorry. No. I had something to do. Now, quantized inertia, from my understanding, I've been viewing a video about it, and quantized inertia would be a phenomenon by which movement creates event horizons that differ from your back to your forward. So if you look back, there are certain lights that you will not see, but since you're accelerating in that direction, there are certain lights that you can see more in front of you. In other words, you are losing some of your event horizon on the back, and you're gaining some on the forward part. Did you read about quantized inertia, Peter, while I was gone?
Yes. I mean, it's interesting. I'm not this is very much a meeting of general relativity and light. I'm not much of an expert in general relativity to be able to make any educated comment on this. I would only say that yes. Well, there's nothing.
You should
much
check it out because there's a twist then, because they say that there are photon and anti-photon pairs that are born from nothing and they eliminate, and they say it's going to be different in your backward direction than in your forward, because there are going to be some events of creation of matter that will happen more forward than backward, and ultimately this gives an explanation of inertia. There's more creation of matter in a direction rather than the other.
Well, I would say there are mechanisms by which inertia can already be explained with classical electromagnetism, rather than even getting into the crazy quantum. In Jackson's electromagnetism textbook, he actually explains how there's a self-interaction between the light that is mediated out of the a charged particle as it's moving, and that light interacts back on itself and ultimately gives rise to inertia. And you can derive the inertial mass of objects. It seems that this would be an unnecessary complication. Now, I would need to try to understand what would be the mechanism of how an anti-photon would be created. This seems a little bit interesting.
All right. Well, let's talk about it in the future. Bill?
I can clarify something about this inertia deal, but I'll do it rationally. I won't do it with irrational nonsense. If you put up 111 Birdsbeak linear regime, can you put that one up there?
Yep, here it is.
Okay, if you can make that a little bigger, it would be great.
I don't think I can, unfortunately.
Oh, okay.
Maybe I can try this.
if every atom from the sun is connected to every atom of Proxima Centauri, that's our nearest star, 4.3 light years away. If all these atoms are interconnected by ropes, okay, here we have all the stars in a given region of the sun, of the sky, and they're all interconnected. Well, if you have in that case, we have the Enterprise there trying to get out of the sun, out of the solar system. Well, in the Bird's Beak area there, we would have gravitation that it can be described by Newtonian, by the Newtonian equation. But when you get into this linear region, which will come up here in a second, see, it goes into the linear region, and then gravity is not the same in that region as it was in the Bird's Beak. So now you have inertia in front of you, because what happens is you've exited the Newtonian region, the Newtonian range, which is only in the Bird's Beak. That would explain, for example, why the pioneers are slowing down. As soon as any object wants to leave the solar system, it is going to go through that from that Bird's Beak to the linear region, to the linear regime.
But how can there be a Bird's Beak if all of the atoms are linked linearly?
They're linked. Well, imagine you and I are holding many ropes, right, in our hands. The farther you get away, the more the ropes will, in the center between us. You'll have a region where all the ropes converge and act as a single coaxial. That's my point.
Okay.
You can't avoid it. It's a physical necessity. And so what I'm saying is gravity, the square root, the square of the distance factor is only in the Bird's Beak region of the solar system. Once you get in the region between two stars, you get into this linear region, you no longer have the acceleration that Newton and Einstein predicted with their equations. And that's why neither one of those equations can predict why the pioneers are slowing down. They had to invent the nonsense, absolute nonsense, that these probes, because of their irregular shapes, they're throwing heat in front of them, and that's what's slowing them down towards the sun. But it turns out that the Cassini probe, the Galileo probe, they're all doing the same thing. And they can't be that all of them have the same problem with heat in front of them. This is any probe trying to leave the solar system, because every atom of the probe is tied to the sun, and because every atom of the sun is tied to every atom that makes Proxima Centauri, they would have to go from the Bird's Beak into the linear region and slow down. That's why that would explain this inertial deal that this guy came up with.
One thing I found myself wondering today was, do you agree with gravity being proportional in force to the square of the distance, or do you think that becomes wrong at certain scales?
In the linear region, it's not true.
So it's not even true when we're close that it's r squared?
It's close to the sun. It's very it is r squared. In our region, we have r squared, no problem. It's
but
not.
Do you think that when we get away, does it get closer to r or closer to r3? In other words, gravity, the force of gravity seems to diminish as you get distant from the object. Is that diminishment a square function purely and forever up to the end of the universe, or do you think that it's not square?
Only in the Bird's Beak.
Only in the Bird's Beak.
Only in the Bird's Beak do we have Newtonian gravity and Einstein gravity. When you get into the linear region, we no longer have Newtonian or Einsteinian gravity. It can't be.
All right. Wonderful.
Well,
was there any... Peter, go ahead.
I guess besides, this is too high IQ for me to interpret in terms of bird beaks, but if we put that to the side... to answer your question, JF, your chart, the linear, your model, your question about is it goes more than 1 over r squared at larger distances. I guess you were alluding to something like why we observe dark is an alternative to dark matter interpretations. Why the force goes differently. I'm not quite sure why you have this thought in the first place. that
I don't know. I guess it emerged
when
when I was looking at these YouTube videos about dark matter precisely,
right.
and they were like, there was some missing gravity, and I was wondering, what do we know about how the force of gravity diminishes with distance?
I do know that it's been the alternate gravity only, where the gravitational force alters at different distances. Like it's a sort of a scalable parameter, has been played with in the past. I don't know it's not my expertise to know exactly why, but for at least the community doesn't think that it's a valid, that for some reason doesn't work. Interpret that as you may.
All right, wonderful. Was there anything else you guys wanted to discuss tonight? Because I have the clou du spectacle. I have a last reveal that I want to do to trigger Bill. I think that by showing him this image, he will go absolutely insane.
Well, I do want to get to that now, but that's exciting to me. But JF, do we have time to look at some of the things that I sent to you? Or
absolutely. Let's look into it. Did I forget to download them? You send them to me?
I sent you links, hyperlinks, so I don't think they should be.
Oh yeah. I remember. I loaded them. Here they are. So what did you want to look at first?
So let's take a look at, for example, my comment about black holes. My one criticism about the meme. Sure.
All right, here it is.
So here we have
saying until we can feasibly probe black holes at the length and time scales of their dynamic behavior, they remain a topic of mathematical speculation. That is your statement?
Yes, and this is a small brain interpretation, yes. And then there's this Freeman Dyson who comments on both Feynman and not Feynman, sorry, Einstein, and I think it's Oppenheimer on the interpretation of black holes, where he says that they were not particularly interested in it, but they said it's a thing of mathematical beauty. Now we have Bill Gade here, who ridicules mathematical physics, but for some reason he proceeds to develop a theory of that describes what is the pinnacle of mathematical physics. This is a circle that I haven't quite figured out how to square yet.
It's true, Bill. You are invoking mathematical concepts intuitively by referring to the rope, the pull, the push.
Well, let's put it in the proper context. The context is as follows. Mathematics has no power to explain anything, any phenomenon. That's the first thing we have to get clear. An equation can only describe. The physical interpretation is the big problem today. We're not contesting, we're not challenging the mathematics. We're saying we need to have a physical interpretation for how a pen falls to the floor. We need to have a physical interpretation how a magnet attracts another. We don't have these today. So the issue is not to continue developing more math. The issue is we need to figure out what the mechanism that Mother Nature uses to produce these effects. That's what I'm looking at. I'm saying we need to conceptualize these things. We don't need to observe anything. We don't need to measure anything. We don't need to do any more of that. What we need to do is conceptualize and say, how does Mother Nature perform all these things? And if we're going to say mass pulls, the mass of a black hole pulls on a star, we're using magic. We're not explaining it. We're just saying, look, there's this, when the elephant is very big, it pulls stronger. That's all we're saying when we say mass. We need to have a physical mechanism. It's got to be an elongated mediator. It cannot be anything other than an elongated mediator. And a rope is a good mediator.
Now, Bill, I actually do, as I mentioned last time, I do agree that a real interpretation, I would say, of what's going on, of the dynamics of what's going on in these circumstances work. So now, if you could pull up actually just the one might be good enough for today. There we go. So this is a real interpretation that has been that has been done in a few labs, including Bush's lab at MIT. So if you want to go ahead and play that from the beginning.
All right, here it is.
So now we have these bouncing balls here, or bouncing oil droplets that you can interpret as, say, your charged particles bouncing on your fabric.
And that's oil bouncing on water?
It's oil droplets bouncing on oil on a vibrating disc.
Wow.
And this has actually been performed in the lab, so this is quite amazing. And that's a fast scan of a much faster speed bouncing of these oil droplets that you see here. And the key mechanism is that these oil droplets, when they bounce, they produce the waves. And there you have entangled particles, for example. But the key mechanism is the ball bounces. Here's the mechanism. If you want to pause it for a second, the key mechanism is that the oil droplet disturbs the water, the oil around it, and produces a vibration or a wave in the shaker in the liquid, and then as a result, when it comes up and then bounces down again, it's going to move in a particular direction depending on where it lands with respect to the waves that it already created.
This is fascinating. But this is this meant as a model of what happens in quantum physics while it doesn't happen with oil?
Right. This is exactly.
So what is the oil supposed to be an analogy of?
The oil.
The ocean. The ocean.
The ocean is interpreted to be the potential, the electromagnetic potential that.
I'm talking about physical objects. Tell me, speak objects. Don't tell
voltage.
me mathematical concepts.
I'm not. I'm sorry. Can you repeat that? This doesn't make sense.
I don't want you using any word of mathematics. I want you to use physical object. What is the oil an analogy of? What is the
photons
oil in terms of the medium?
The photons.
Huh?
The photons.
No. We still don't. We're still not talking in the same.
See the photons.
You're saying there's this ball that's going up and down, right? This oil droplet. Right? And it's going up and down in some kind of ocean there. You show
an ocean of photons.
I'm sorry?
An ocean of photons.
Ocean of photons. Okay, so that means all these photons are discrete particles. Am I right here?
It can be an
elongated. They are. It's a yes or no.
I mean, you want to get more granular. We don't need to get granular here, Bill. But
well, I do want to get. I want to get to the bottom of it. I want to know if all that ocean of oil, are those discrete particles or are they interconnected? That's what I want to know.
Are they interconnected?
Those photon particle. What is the medium that surrounds the photon particles? Each photon, what is it surrounded by? Each photon particle.
No, the electrons are the oil droplets that are bouncing.
Yeah, and the ocean. I'm concerned about the ocean. Forget about the oil part. I want to look at this ocean, this magical ocean that you have there.
It's magical, Bill. I can go to the hardware store. Bill, I can go to the hardware store and get oil here. I'm not sure what the problem here is.
It's magical when applied to quantum. It's magical when we say there's an ocean around an atom or whatever. What is the medium that keeps an electron tied to a proton? That's what I'm looking at. I'm looking at this field, this magical word that is used in quantum mechanics. This field, this region in where everything floats.
Bill, that was a real experiment that was performed. If we can get back to it.
I have no problem with the experiment. I want to know how you apply this analogy to quantum. That's what I want you to tell me.
So
what is the ocean?
The wave is the electromagnetic potential.
There's no such word as potential in science. So that's a
okay. So
religion.
what would you like? What would you like to?
I want a physical. I want a tree. I want a rock. I want a dog. I want a physical object.
Then if you want, then we can call it the liquid.
The fabric.
The liquid or the fabric.
Yeah, but the liquid there, you have a two-dimensional. You have this ball floating in a two-dimensional scenario.
Sure.
Here we know that the region around an atom has to be three-dimensional.
Well, I mean, on the surface of a metal, for example, you have, for example, charged particles moving around the surface, and you have surface charges. So, I mean, we're not always confined to three dimensionals. That's the first thing I should mention. Now,
is there three dimensions around an atom?
I know you don't like to abstract, Bill.
No, it's not a question of abstract. I need to conceptualize this.
Conceptualize.
I need to find out if I have an atom, the region around it has to be three-dimensional.
Right.
Okay, so now how do you put your two-dimensional surface onto this three-dimensional scenario? That's what I want you to conceptualize for me.
This is a difficult thing to do.
It's
not impossible. It's not
You're
impossible.
talking about flat land, and I'm talking about solid land.
So, Bill, in other words, you're saying that Peter, with his oil, he's a good performance artist, but not a physicist.
I have no problem with the experiment that he did. No problem whatsoever. I'm just saying we cannot
I didn't do it, but
analogy what happens around an atom. Or we cannot say that this oil, which is a two-dimensional scenario, is what the ether in the universe is made of, or the ether around an atom, or whatever. The world is three-dimensional. We have to identify what physical objects are in that invisible three-dimensional world. This two-dimensional scenario cannot be extrapolated to our three-dimensional world. Otherwise, you got to identify that three-dimensional ocean.
The problem, Bill, is that with the oil droplet experiment, we're utilizing gravity in a unique way. The reason why it doesn't work is not because of some missing link in our system, but precisely because we don't have gravity, say, for example, working in this way. Now, if we had, for example, we used some sort of charged fluid, for example, and we use some sort of background charge, for example, it would probably be crazy voltages that you need to apply inside this three-dimensional sea. And you say charged the sides and then shaked these, it created noise that created this sort of wave around it. I might imagine that you could, or a bubble of waves around it. It doesn't seem far-fetched to be able to extend this analogy within a physical setup. I just wanted to point this out in that it's very neat what Bill's developed. I just want to point out that it's actually, this is how instead of comparing it to the waves and particles, I think Bill's ropes are much more suited to, say, be compared to oil and oil droplets in terms of where it lies in the realm of physics.
All right.
I'm curious what you think about that, JF.
Well, I mean, I cannot take a conclusion on this freaking case. That's why I keep having Bill on. There seems to be nothing that will stop Bill. He can adjust his explanation to everything, and now he's asking me to leave dark matter and marry the rope. It's a tough decision. I'm very emotional with these things. I will say I've never seen any sort of alternative thinking framework that is so malleable to the point of explaining everything and potentially more than current physics. So that's why I keep having Bill on. It's stunning. And in any case, even if it was wrong, it is good thinking that helps the mind to try bold ideas. And that's what we need in physics anyway.
Precisely.
Right?
I do agree with you. I do agree with you there, JF. This is one. I think more people should explore these, I would say, heterodox ideas, these different what I would call different ways of philosophically approaching science, as opposed to the orthodox pedagogy. I think only then can one advance and try to understand more about the reality we live in.
All right, now,
JF,
yes.
I'd like to answer that fellow who asked that question earlier.
Oh, yes. Let me reread the question here.
I don't want to leave him dangling.
So Fizzes was asking, what substance are ropes made of? And how can you prove it and observe it? Don't try to deflect the question with bullshit about how you don't need to prove it.
Well, first of all, let me address that last part first. In science, we don't prove. Prove means I'm going to twist your arm and convince you and try to make you believe like I do. So we don't do that in science. Science, we explain for you to understand, and then we leave it at that. What you believe is your own personal business. So there's no proof. And I'm not going to prove to him anything. What I'm going to do is the following. I'm going to explain to him what the model is. The model is that a rope is really, if we were to untangle every atom, every rope in the universe, we would have a single closed loop thread. Okay? So I'm saying the entire matter in the universe consists of one single closed loop thread. Think of it as a circle. Okay? That's the best probably image that you have. Okay, so ultimately that's all there is in the universe. Now, this thread winds around, turns into atoms and ropes that interconnect the atoms. That's it. That's all that is in matter. So if we were to unravel every atom, every rope, all we would have in the entire universe is one thread. The thread is an elementary entity. An elementary entity, by definition, or fundamental entity, is one which is not made of any constituent parts. It's a single closed loop thread that's made of a single piece, but it has the ability to be flexible, unlike what we have in our macro world, where we say, well, if something is made of a single piece, it's not flexible, it's not malleable. This thread is made of a single piece, and therefore it's not made of anything itself, because by definition or the assumption is that this thread makes up everything else. Okay, so that's the answer to his question.
Hey, Bill. One thing that I didn't get to clarify last. Perhaps you already did clarify. When you have, say, four particles here, so when you have rope interacting with all of them, and let's say this is the polarization problem that I didn't quite understand. If I start rotating, say, two of these particles with respect to each other, do you predict that when there's going to be a tangling of these ropes?
I don't do predictions. Sorry.
No, I'm not asking you. Can you please describe what happens?
I can explain.
When two particles over here are rotating.
Yeah.
Are rotating with respect to there, and there is another pair over there where there is ropes connected. They're going to get tangled up. Aha!
Tangling. You want an answer to tangling?
I want an answer into tangling, Bill, because
of course. Now the first question I've got, because everybody of course thinks of the tangling issue. Oh, all these ropes out there, don't they tangle? And the first answer to that is, well, why didn't you ask the question in quantum? Quantum has the idiocy of a particle being at two places at once. It's known as decoherence. Hold it. And then it also has where two particles can be at the same place. It's called superposition. Nobody questions that. Well,
Bill, I would say this: the wave. If you go back to the picture that I showed before, where you have a bouncing oil droplet, where you have. If you notice, the wave is actually dispersed long in further distance than where the oil droplet itself is. As a result, it can be in two. It can go through the wave itself can go through both slits. To take the analogy further, however, the oil droplet only goes through one, and the result of the wave going through allows gives additional possibilities of where the oil droplet can bounce. So I don't see a contradiction if you use that.
Well, the contradiction is that you use the magic wand. That's where the contradiction is.
Where's the wand?
The wand is that you turn your particle, your discrete particle, into a wave to get your case done.
There's no magic there.
Waves are particles. Can a particle be at two places at once? That's the question. Particle.
We describe the particle as the wave.
As the wave
combined with the water wave combined with what people ordinarily describe as particle wave duality, as is the particle with the wave.
Cheating. It's known as cheating.
It's not, fine, but if you want to use if you want to use a language interpreted using what's called pilot wave theory, which is what I was presenting here, and that was a particular formulation. The oil droplet is a physical analogy of it. You have a particle in a real physical mediated wave, and the particle is just in one spot, but the wave can be in multiple positions.
Right, I know. That's what quantum did. They brought in duality. They said, look, let's just merge the particle with the wave. And when we got to explain this, we'll use the particle. And when we want to explain that, we'll just use the wave. And that's the problem. That's cheating. It's known as cheating because you don't have a physical interpretation if you're going to use the particle as a wave whenever, it's convenient. That's ad hoc.
Well, Bill, I hope maybe take a look at that the oil droplet analogy further, and then maybe you can comment more on this later. I didn't mean to throw this at you. I think there's more to it than you're appreciating.
I looked at it this afternoon, and again, my only question with that, right off the top,
the 3-dimension.
Was that you got to interpret? You got to show what the analogy is of that 2-dimensional up and down surface to a 3-dimensional, solid land. What I call.
Yes, but I would say it does solve the problem that you might have with particle wave duality.
To solve that problem, we need to start at language, semantics. That's where we have to start.
Semantics, yes, which is the philosophy. Which
words mean.
I didn't mean to belittle that last time. It's an important topic, but it's more. It's not physics. It is, I would say, a difficult portion of philosophy and metaphysics of the physics we're describing.
I disagree. I'm saying we have to establish the foundations of physics. No one has done that in 10,000 years. Nobody knows what physics is about. That's the problem.
That is true.
Objects.
You're mixing.
Has to do with you can't do physics without objects. Therefore, you need to define, for the discipline known as physics, you need to define what an object is and separate it from concepts. And mathematics and physics only works with concepts, positive, negative, wave. All that is nonsense. That has mass. None of that has anything to do with physics. Physics only works with objects.
To that, I would say that you're right in that we do need to deal with objects. There are difficulties in that we've tried to measure, say, the size of the electron, and we still haven't figured out what the size is. I know you have an answer to that, which is actually a pretty clever one, which is why I like the rope hypothesis for that reason. One of the many reasons. But I would say you are mixing metaphysics with physics. This is what how I would answer that. Don't
you need foundations for physics? Yes or no?
It's like yes, you do need foundations, but it was not. But but yes, you're absolutely right. But other people are going to have different metaphysics because physics cannot answer questions about metaphysics. Is what I'm going to say. So please stop mixing. It's just like you're mixing a biology with a biologicalism in a sense, sort of the metaphysics of biology. You want to include both, but let's not mix the two up and say they're the same thing.
I'm not saying that we mix them. I'm saying that for the way physics has developed, it developed along mathematics. And today we have this erroneous view of physics that it's about mathematics. It's not. Physics
Right.
is about objects. And so we have to
Sure.
establish what physics is about. And that's got nothing to do with metaphysics or philosophy. It's got to do with establishing the foundations of physics.
Right. Until we
that's
find
not
out that.
philosophy.
No, I agree. I agree with you there.
You know,
Yeah, the
we need to
reason I'm
define-
very welcoming of Bill's view here is that I agree that that essentially a science needs to define what's its subject, and it cannot define two subjects. It must start with one thing that it studies. And I fully agree that in physics, it's not really specified. I've never heard it specified by anyone else than Bill himself. Now, Bill, I was wondering, it passed through my head. What do you think when Lawrence Krauss says something from nothing?
Well, again, that's magic. That's you gave a good example. I mean, is that physics, or are we talking religion now?
Well,
You know, I mean, what is that?
Well, Bill, I mean, you should keep in mind, Bill, that you treat physics as if it's some sort of uniform block. Most people, most physicists, actually are quite critical of Lawrence Krauss's liberal use of the word nothing.
I don't think that's true, Peter. I'm going to be honest with you.
I have
the majority
experience to say suggest otherwise.
Okay, maybe you do because you're closer to those people. I'm not going to dispute that. I have a different opinion. Let me tell you why. What reaches the public, that's what I'm concerned about. I don't care what I don't care what the Harvard people think or the Cambridge people think. I want to know what the public thinks. And the public at large believes black holes as being true and proven and no chance of ever turning that back. They believe in dark matter. It's presented as proof and truth to them. So the public believes in all these things. And that's what I'm concerned about. If the mathematician would present it to the public saying, look, this is speculative. We don't really know. But that's not the way they present it. They say, we've proven black hole. We've seen them. We know they collided and sent gravity. They talk about it as proof and truth. And that's what the public believes. That's the problem.
I completely agree with you here, Bill. It's kind of a problem of the squeakiest wheel gets the oil. And the squeaky wheels in these scenarios are abusing language and they are abusing concepts. And I completely agree with you there.
All right, gentlemen, we are headed toward our conclusion. I will pull my last move on Bill, and I will be singing a song from Rage Against the Machine, and who was it before Rage Against the Machine? I don't even remember. I will be dancing on the grave of the rope theory because I'm about to present a graph that will trigger Bill Gade. 1, 2, 3, go. Here is something you can't understand. Here is something you can't understand. I can get a Higgs boson. Here is something you can't understand, Bill. I can get a Higgs boson. Here is something you can't understand. What do you have to say to this graph, Bill?
Love it. How much does it cost to buy your long play?
All right, gentlemen, it was a pleasure. I'll be continuing the show alone. I have some news to cover. Thank you so much for coming. Peter?
Hey, if there's just one thing I would like to say at the end is I hope that we continue to put aside petty human squabbles that we get involved with on a daily basis. And I hope that tonight's discussion helped us illuminate the truth about a reality that we can pass on to our future AI overlords, as predicted by JF's new book, The Revolutionary Phenotype, available on Amazon.com nearest you.
Thank you so much. Bill, thank you for coming. Bye-bye.
Yeah, bye-bye.
All right, that was exciting. Again, these discussions are so fascinating. What is there to say after this? Erdarbrenner says rope. And he says, that feel when I'm smarter than these scientists. Arnold Nicotina says, this has completely turned me off of pursuing any education in physics. JF, I understand now why you no longer work in the science industry. Well, I think that these discussions are fascinating when we test these frameworks. Personally, it's not the kind of discussion that got me out of academia. It's precisely the contrary. It is the assumption that something is wrong without proper challenge. That is what hurts me. Hurts what I think sends $10. He says, these shows are so much fun. Machiavelliscus says, did Einstein prove time travel is possible? Well, in a sense, yes. You can view dilation of time as an effect of a type of time travel. But it's just a type, and it just gets you into the future with respect to other people who don't travel as fast as you. Francis Varnick says, Bill, how do you explain heat mechanistically? I think that Bill has, the reason I didn't take the time to ask is that it was already getting long, and Bill has a traditional view of heat. In other words, his rope theory doesn't say anything special about heat. As far as I know, you can have his ropes just shaking, just having energy. Well, it's true that he probably wouldn't use the word energy, so maybe I can ask him next time. Farmmaster Ferrer says, thoughts on theoretically using general relativity to travel forward in time, such as a particle moving at a fraction of light speed to dilate time. Yeah, it must exist. But the question is, how much energy can we use to get there? And the big problem is also the effect of accelerational effects of gravity. Getting to the speed of light, you will need to undergo 6G, 7G type of acceleration for a long, long time. Maybe with a frozen body it would work, but the faster you get to the speed of light, the more you have difficulties because it crushes your body, and you cannot handle more than 1G in a prolonged fashion, maybe 2G in extreme cases, but you'll need to be frozen if you go for 3, 4, 5G.